Alright, so we're gonna be talking about AC and DC generators tonight. Just bear with me, I know this shit's boring, but it is what it is, right? Alright, so we know that voltage is induced when when a conductor cuts the magnetic field, right? You know, we learned about that with the inductors. Current will flow when the circuit is complete. The current direction is determined by the direction of the flux lines and the direction of the conductor's movement through the flux. Current direction may be found by the left-hand rule. Remember, if there's no motion, there is no current. An electric generator is a device that converts mechanical energy to electrical energy. It's a mechanical to electrical transducer. What's something that converts electrical energy into mechanical energy? Motor. The motor is just a generator that's backwards, right? You know? The generator takes mechanical energy, which is the the gears turning, whatever, pulleys turning, whatever, and takes that and converts that into electrical energy. Motor is going to take electrical energy by your line voltage and convert that into usable mechanical energy. Voltage is generated or induced across a conductor while magnetic lines are cut. Current is electron current, not conventional current. And here's the left-hand rule. The thumb indicates the direction of motion. Your forefinger is the magnetic field of flux, and your middle finger is the direction of the current flow. Alright, so here we've got a wire loop between in the magnetic field. Alright, so if that conductor is sitting at 0 degrees, the wire loop is moving parallel to the lines of force. No lines of force or flux are being cut, therefore no voltage is being induced across the coil. When that conductor is at 90 degrees, that means maximum lines of force are being cut and maximum voltage is being induced. As seen below, the coil output voltage is AC. DC output can be achieved by mechanical polarity switching. Commutating the output of an AC armature. A commutator is a segmented ring, the segments of which are connected to the armature windings. Brushes are contacts that ride on the commutator segments as the armature rotates. They carry the voltage from the armature. Commutator and brush orientation is such that the brushes switch AC to pulsating DC. output from a DC commutator is a pulsating DC voltage. You can see in the bottom right picture that it never crosses that zero line. It's staying zero to whatever the top is. Alright, generator components. Got the armature windings, the brushes, the field windings, and pole pieces. There are 3 armature winding configurations: lap winding, wave winding, frog leg winding. Parallel windings increase the current capacity. Series windings increase the voltage output. Combination series and parallel increases both current capacity as well as the voltage. Alright, so top one is the lap winding, middle is the wave winding, and the bottom is the frog leg winding. Armature windings are labeled A1 and A2. Interconnections are made through the brushes. Lap wound armatures provide high current at a low voltage output. An example of this is a welding machine. Wave wound armatures provide a high voltage at a low current output. And frog leg wound armatures are a combination of lap and wave for moderate voltage and current output. So the brushes ride on the commutator as the armature rotates. Brushes transfer energy from the rotating armature coils to fixed contact points for connection to the outside world. This is a picture of carbon brushes riding on a DC commutator. Most brushes are carbon-based materials. They slowly wear away as the commutator wipes against them, dramatically reducing the need for commutator replacement. Heat of friction, arcing, and resistance do not easily harm carbon brushes. Carbon brushes develop a thin, slick contact surface that enhances conductivity with copper commutators, and most brushes are easily replaced. The field windings provide the magnetic field through which the armature rotates in order to develop voltage. In a generator with a rotating armature, the field is stationary, it does not move. The field is called the stator winding. Field magnetism is created by an electric current. In small generators, the field might be created using permanent magnets. The field current must be DC. In DC generators, the field winding may be powered by the armature. Shunt field windings are high impedance windings connected across the armature. Series field windings are low impedance windings connected in series with the armature. These field winding arrangements rely upon small residual magnetism to get the generating process started. Stator field windings can be either shunt or series. The purpose of the field is to produce the magnetic flux. The greater the field current, the greater the flux density, and the greater the voltage induced in the armature. Field current controls regulate generator output voltage. Internal or external automatic control or a manual external control. The field windings are wrapped around pole pieces. Pole pieces may be an electromagnet or a permanent magnet type. Permanent magnets are used for a field permanently mounted in a stator. Here's 4 pole pieces, or 2 pairs are shown. Field windings are wound around these pole pieces. Alright, the generator connection types. Series generators, the field winding is in series with the armature winding. It requires residual magnetism of the field to begin generating. Greater load current increases output voltage due to increasing field current. Output voltage may be controlled by shunting current around the field with a diverter. This is best used with fixed loads. Factors affecting the output voltage are the armature speed in RPMs, load current, armature turns, field turns, diverter adjustment, and the magnetic core saturation. In shunt generators, the field winding is connected in parallel with the armature output. The field winding often relies on residual magnetism to start generating. As the output voltage builds, field current increases, necessitating a regulator circuit. Heavier loads reduce generator output voltage, necessitating a regulator circuit. Regulators used to adjust the amount of current through the shunt field, thereby controlling the output voltage. Your field current regulators can be a simple electric or a complex electronic device. Compound generators incorporate a series field winding and a shunt field winding. The shunt field assures rated voltage output at no load condition. The series field assures rated voltage output at a full load condition. There is a long shunt compound generator and a short shunt compound generator. An compounded configuration generator results in a full load output that is higher than the no load output. A flat compounded configuration results in the full load output is equal to the no load output. Under compounded, the full load is less than the no load. And differential compounded, full load output drops dramatically from no load output. A generator is a transducer. It converts mechanical power to electric power, heat power, and other forms of power. Generator loss refers to the portion of mechanical input power that is converted to forms of power other than electric. The efficiency of a generator is found by dividing the power output by the power input. Alright, so different generator losses you have, windage losses, resistance losses, friction losses in bearings and commutators. The reaction at the armature. Armature current occurs when a load is connected, causes a magnetic field to form around the armature. The armature flux interacts with and distorts the field flux and causes commutation, which is arcing between the commutator segments. This shows the twisting of the magnetic field because the current in the armature creates an armature reaction. Compensating windings offset the effects of the field distortion. They keep the neutral plane properly aligned and placed between the main field poles and wired in series with the load. They're also known as compensating windings, interpole windings, Thomson-Ryan windings. Parallel and DC generators may be used to increase the current capacity. They must have identical operating characteristics, must be connected identically, and must incorporate an equalizer connection. Without an equalizer, one generator may act as a DC motor. AC generators. They operate on the same principles as a DC generator, often called an alternator. It requires a field magnet, which can be permanent or electromagnetic. It requires slip rings and brushes rather than a commutator and brushes. That's very important. You'll see that several times on tests and all that shit. Know that a DC generator is going to have a commutator, and AC generator's got slip rings. Blah, blah, blah. Construction of AC generator requires the means of passing a conductor through a magnetic field and slip rings to move AC current from the armature to the outside world. There are two types of AC generators. The rotating armature, which slip rings extract output current, is primarily used for lower power applications. The rotating field, the slip rings supply DC to the rotating field and is primarily used for high power applications. In a three-phase AC generator alternator, three armature windings are spaced 120 degrees apart. Slip rings are required for each output phase. This revolving armature three-phase generator uses three coils spaced 120 degrees apart, connected in a Y pattern. The 320 degree spaced outputs are generally designated A, B, and C phase. Output through slip rings restricts current capacity. The rotation of heavy armature generates a lot of heat and creates dissipation problems. Here's a graphic representation of three-phase voltage production. You'll notice each phase, they're 120 degrees out of phase with each other. Alright, in revolving field AC generators, the armature is on the stator, the field is on the rotor. The armature windings are cut by the rotating field. Only low DC current passes through slip rings to the rotating field. The mass of the static armature does not restrict voltage or current output. And here's the three phases now mounted on the stator of a rotating field generator. In a revolving field AC generator, Each of the three phases has two coils 180 degrees apart. These three phases are mounted 120 degrees apart. The wiring configuration shows one end of phase A, B, and C connected with the other. Phase A and B, B and C, C to A. Alright, there are two rotor types, the salient pole rotor and the round rotor, or turbo rotor. The salient pole rotor, used at major power generating facilities such as hydroelectric plants. Characteristics of the poles are big, heavy, rotate very slowly, experience air drag, and have individual field wirings. Now here's the rotor of a rotating field generator using the salient pole construction. Round rotor construction, the round rotor poles are flush with a rotor curvature. Round rotors do not present much air resistance, rotate at a high speed, and the round rotor windings are not visible. The excitation systems. Permanent magnet fields are used in permanent magnet generators. They're used as the stationary field of the permanent magnet generators. The shaft speed controls the generator output frequency. The output voltage is externally controlled. Permanent magnet generators are only useful for low power applications. Here's an example of a permanent magnet rotor. The stator of the permanent magnet generator has permanent magnets on the stationary portion. The fixed exciter. Field current is initially unregulated. Output from a generator is initially unregulated. Generator output is connected to a regulator that samples the generator output and closely controls the generator field current. To bring the generator output under control and accurately regulate the generator output voltage. Rotating exciters may be mounted separately on the same shaft or on the same shaft as the main generator. If it's on the same shaft as the main generator, AC output from the rotating exciter armature is rectified and applied directly to the main generator rotating field with no brushes. System output voltage is controlled by control of the exciter field. Alright, so with all this voltage being induced, we're going to create a lot of heat, right? So we got to keep our generators cool. It's done by, in small generators, it's natural ventilation or built-in fans. In large generators, they may employ hydrogen atmosphere cooling.
What about forms of liquid cooling?
Getting there. Getting there.
Okay.
Alright, fan mounting. The fan is mounted onto the shaft under the housing at the left. The fan blows air over the ribbed housing to cool the generator of heat. Why is motors, generators, why are they all made like that with the ribs?
That helps dissipate the heat.
Right, that's just a heat
It's a
sink.
heat sink, yeah, on the computer.
All that does, that's increasing surface area to allow it to cool more quickly. Alan said there are some generators that are liquid cooled. the bigger generators. Man, at the end of the day, it's, just take like, the big generators at Facebook, right? You know, those are, all the fuck that is damn big ass diesel motor turning all this shit, right? You know, it's got, you know, coolant and everything else running through it, cause it is a motor, right? If you don't have coolant for your car, what happens? Right.
Those have oil and all kinds of stuff, like, it's just like a car and truck.
The AC generator output frequency is determined by the number of poles and the rotating speed in RPMs. Alright, so, important formula here. Frequency equals the speed times the number of poles divided by 120. And that 120 is just a constant. I have no idea where it comes from. It's just part of the formula. Alright, so let's say you just want to solve for the speed. What would that be?
The rotations.
Now, I mean, what would be the formula to solve for speed? S equals what?
Is it P times 120?
P over 120 times F. The frequency.
P times what? P times
P
120?
over 120.
No. Alright, so if we're gonna solve for S in this equation, first thing you're gonna do is multiply both sides by 120, right? That way we get that 120 out of the bottom, right? So now we've got 120F equals S times P. And then we'll just divide both sides by P and get 120F over P equals S. So your homework, it asks for, I think there's like 3 questions, one asking for the frequency, one asking for the speed, one asking for the poles. Did everyone understand how we manipulated that equation? Everyone good? When we get through, I'll put it up on the board too. Factors determining the generator output voltage. The length of the armature conductor that cuts the field flux lines, the speed of rotation, and the field flux density, or the strength of the magnetic field. When frequency and armature size are fixed, only field flux density can control output voltage through field current regulation. If an alternator has no mechanical or electrical limits, the only factor limiting alternator output is mechanical input power. Alright, 3-phase generators may be paralleled if the following conditions are met. The voltage outputs are identical. The frequencies are matched. A, B, and C phase peak and sync. Multiple methods may be used to verify these conditions. Failure to verify these conditions can result in dangerous or even explosive results. Techniques for verifying synchronous generator operation, phase rotation indicator, the 3-lamp method, and a synchroscope. Alright.